Hello, my name is Reagan Smith, and this is my presentation on decoding the copper-silver alloy. So just to start off, I wanted to talk about the phase analysis at 900 degrees Celsius. So first off, that puts us at this green dot here, which is in two phases, solid and liquid. The composition of each phase is the liquid phase is 59% by weight Cu, and the solid phase, which is represented here, is 93% by weight Cu. That's shown on these lines drawn onto the chart. And then the weight fraction calculation using the lever rule is shown here, where the liquidus phase is 38% and the solidus phase is 61%. This phase diagram helps guide these calculations by explaining the relationship between the different phases, temperature, and percent of weight and percent of solid, liquid, or other phases on this chart. And the lever rule overall helps you to figure out what percentage of which metal is solid or liquid at a given point, as shown here. Okay, for the heat treatments, just going over what normalizing and annealing do to each one. The normalizing option will refine the grain size of the microstructure, making it more refined sizes, more consistent. The annealing will increase the grain size, and the normalizing will change the mechanical properties by making it stronger, harder, and a balance between ductile and strength, whereas annealing will make it much more ductile but a bit weaker, and much softer than before. So these two processes have very different results. Slow cooling has a different grain effect than rapid cooling because slow cooling creates larger grains and fast cooling creates smaller grains. And when there are smaller grains, they have less distance that they can move, which makes them tougher, whereas the larger grains can act in a more ductile and softer way because they have more room. The grain size, as I said before, changes strength and ductility, with larger grains as more ductile and weaker metals, and smaller grains less ductile and stronger because they have less ability to move. And then finally, for material composition optimization, on here it wants a strength that is over 20 MPa stronger, but a ductility that's still above 38%. So I've got the 2 points there marked on the graph. The ideal concentration is anywhere between 72% and 57% silver, or 28% and 43% of Cu. And modifying this composition, as you can see on the charts here, allows for the as the Cu percentage goes up, it gets stronger, but as the Cu percentage goes down, it actually gets more ductile. So finding that balance between those 2 points on the graph. The way that I would change this percentage with the solid materials and the furnace is simply to heat the solid materials at the given weights to a liquid and combine them with the mixture and make sure that they become a homogeneous mixture before allowing it to cool again. And then again, we would be able to look at the fast cooling or slow cooling processes to ensure that it still has the correct ductility and strength properties. This was my presentation. Thank you.